What I do with the compartment diagram is you have two quantities, x1 and x2, and maybe something's going into x1, so x1 is increasing at this value I, and then x1 is decreasing at a rate of c times x1 is what's going out, minus a times x1 is what's going out over to x2. But it's also increasing at b times x2 flowing into x1. Similarly, x2 is decreasing at b times x2 and d times x2 and increasing at a times x1. So the differential equations for x1, so the rate of change of x1 with respect to t, dx1 dt, is positive I plus bx2, right? The arrows into it are positive, minus ax1 minus cx1. Similarly, dx2 dt, the rate of change of x2 is positive x1, right? That's going into it, minus bx2 minus dx2. So we have this sort of compartment set up, and then we can kind of simplify it a little bit, right, as I minus a plus cx1 plus bx2, and dx2 dt is ax1 minus b plus dx2. And then for most of the linear systems of differential equations we've been looking at, we are assuming that the I value is 0, because, right, if we have this kind of equation where it's just a multiple of x1, a multiple of x2, a multiple of x1, a multiple of x2, there's nowhere for I to be anything other than 0. It doesn't get carried into either of these. So we're supposed to find the compartment model given the differential equations. All this amounts to is setting negative a plus c equal to negative 4, b equal to 0.6, a equal to 4, and b plus d equal to, negative b plus d equal to negative 0.9. So here's what I've got. I've got, in fact, the easy one. So b equals 0.6, a equals 4, and then negative b plus d equals negative 0.9, so b plus d equals 0.9, but b being 0.6 means d equals 0.3, and a plus c equals 4, or negative a plus c equals negative 4. So a plus c equals 4, but a being 4 means c equals 0. So the compartment model for this particular example is going to look like, and we're basically just going to take this and erase a, b, c, d, and x wherever they are. It's going to look like, what have I got here? So, sorry, I wrote, so a, b, shoot, I forget what's what. Oh, but it's easy to figure out. So, right, so what's going out of x is a and c. So this was a, sorry, without going out of x1 is a and c. So a is 4, and c was 0. So we kind of don't draw that arrow if nothing's going out of it. And then what's going out of x2 was b plus d. B is going into x1, so the b value is the 0.6 value, that's right here, and the 0.3 value is right there. So that's what the compartment model looks like. And then to analyze the stability of 0, 0, right? Because again, 0, 0 is an equilibrium. If x1 and x2 are both 0, then dx1 dt and dx2 dt are both 0, meaning it's not changing. So to analyze the stability, we do the usual thing of finding the eigenvalues. Just erase all this. So to analyze the stability, you need none of this. You can just look at this and be like, okay, my matrix is this, negative 4, 0.6, 4, negative 0.9, and then we find the eigenvalues. So we've got, right, so let's do, a minus lambda I is negative 4 minus lambda, 0.6, 4, negative 0.9 minus lambda. These numbers might totally suck, I just made it up. Multiplying this together, I've got negative 4 minus lambda times negative 0.9 minus lambda minus 0.6 times 4, which is equal to, it's supposed to be equal to 0. So negative lambda is lambda squared, and then you've got a minus, so a plus 0.9 lambda and a plus 4 lambda, so you've got a plus 4.9 lambda, and then negative 0.9 times negative 4 is positive 0.36, sorry, 3.6. And then negative 0.6 times 4 is negative 2.4. So you've got lambda squared plus 4.9 lambda plus 0.6 minus 2.4 is 1.2 equal to 0. That's the lambda there. And then I doubt this factors. No, it definitely doesn't factor. So we have to use the quadratic formula, which is going to be super annoying. There is another way to do this, which we'll talk about in class in the future. Using the quadratic formula, I get lambda equal to negative 4.9 plus or minus the square root of b squared, 4.9 squared minus 4 times a times 1.2 all over 2 times a, just 2 times 1. Here's the takeaway. This is negative 4.9 plus or minus the square root of, let's see, 4.9 squared minus 4 times 1 times 1.2. 4.9 squared, gosh, I really don't want. So here's the thing. We could totally calculate this. 4.9 squared is some number, it's almost 25. But 4.9 squared minus 4 times 1 times 1.2 is smaller than 4.9 squared. So whatever this whole quantity is here, it's less than 4.9. Right? Maybe it's like 4 or 3. Right? This is 4.9 squared minus 4 times 1 times 1.2. 4 times 1.2 is 4.8. 4.9 squared minus 4.8. Whatever the number is, it's less than 4.9. So here's the deal. When I do negative 4.9 minus this number, it's going to be negative. So lambda 1 is definitely a negative number. And when I do negative 4.9 plus that number, since that number isn't quite as big as 4.9, like maybe it's negative 4, negative 4.9 plus 4 is still negative. So lambda 2 is also a negative number. And when lambda 1 and lambda 2 are both negative, we know we have a stable equilibrium that is a sink. Sorry, when they're both negative and real, right? So our equilibrium point 0, 0 is a sink, right? Meaning it's stable. And if you want to be convinced of this whole, I would do it for you guys right now, but I can't switch to my screen when I'm doing video recordings. What you should do is you should go to p-plane or whatever it's called, and put in the differential equation dx dt or x prime equals negative 4x plus 0.6y and y prime equals 4x minus 0.9y, and you should see that it's a sink.